A clock on a distant planet does not tick like yours. Time itself is a shapeshifter, bending to the will of speed and gravity in ways that defy common sense. This journey through 30 cosmic revelations will permanently alter how you perceive every passing second. You will discover why time travel to the future is not just possible but proven, how black holes can stretch a minute into a millennium, and why the entire universe might be operating on a quantum stopwatch we cannot hear. Strap into the ultimate time machine because we are about to venture into the heart of spacetime's greatest mysteries. What feels more real to you, the steady tick of a clock or the swirling chaos of the stars? Our own planet provides the first undeniable proof that time is not a constant river flowing at the same speed for everyone. Einstein's theory of relativity shattered the old idea of a single universal clock. He revealed that time is woven together with the three dimensions of space into a single fabric called spacetime. This fabric is not rigid. It can stretch, bend, and warp under the influence of gravity and motion. The faster you move through space, the slower your clock ticks through time. This is not a mechanical error. It is a fundamental property of reality itself. Consider the famous thought experiment of the twins. One twin stays on Earth, living a normal life. The other boards a spaceship and travels to a distant star at a significant fraction of the speed of light. For the traveling twin, years might pass on board, but upon returning to Earth, they would step out to find their sibling decades older. The traveler experienced less time, not because of a faulty clock, but because their high-speed journey literally slowed the passage of time for them relative to everyone else. This twin paradox is a direct consequence of relativity, and this is not just a fascinating idea confined to thought experiments. It is engineering reality. The Global Positioning System, or GPS, in your phone or car relies on a network of satellites orbiting high above Earth. These satellites are moving at tremendous speeds and are in a weaker gravitational field than we are on the surface. Both of these factors cause time on the satellites to run faster than time on the ground. If the satellites' incredibly precise atomic clocks were not constantly corrected for this relativistic time dilation, the entire system would fail within minutes, throwing your navigation off by kilometers every day. Your phone's map works because we must account for the fact that time itself flows differently up there. This bending of time is inseparable from the bending of space. A massive object like our Sun does not simply pull on planets with an invisible force. It actually warps the space-time around it, creating a kind of well. Planets like Earth follow curved paths, what we call orbits, because they are rolling along the contours of this warped fabric. Where space is bent, time is stretched. So the very ground you stand on is a region where time moves slightly slower than in the emptiness of deep space. Your head is literally aging faster than your feet by a minuscule but real amount. This intimate connection between gravity and time, between mass and the ticking of the clock, is the first and most crucial key to unlocking the universe's strangest temporal secrets. If gravity is the universe's master clockmaker, then a black hole is its ultimate time prison. Near the edge of a black hole, at the boundary called the event horizon, gravity becomes so unimaginably strong that it warps space-time into a near standstill. For a hypothetical observer brave or foolish enough to hover just outside that point, time would crawl. A single hour for them could stretch into years, decades, or even centuries for someone watching from a safe distance. Their clock would tick with agonizing slowness, their movements appearing frozen from afar as the ferocious gravity stretched each second into an eternity. This is gravitational time dilation pushed to its absolute extreme, where the fabric of time is pulled so taut it nearly snaps. This effect is not confined to cosmic monsters. It operates on a delicate scale right here on Earth, a whisper of the universe's underlying mechanics. Because gravity is slightly weaker the farther you are from a planet's center, time actually passes faster at higher altitudes. This means the clock in a skyscraper's penthouse ticks a tiny fraction faster than one in the basement. More strikingly, your head is aging faster than your feet. The difference is infinitesimal, far too small for you to ever notice, but it is undeniably real. Scientists measure this using atomic clocks of astonishing precision. In one famous experiment, physicists placed one ultra-precise atomic clock on the floor of a laboratory and another on a table just a meter higher. After running for a while, the clock on the table, experiencing ever so slightly weaker gravity, was measurably ahead of the clock on the floor. The flow of time itself had been altered by a mere change in elevation. To visualize the staggering power of this phenomenon, recall the water world from the film Interstellar named Miller's Planet. Orbiting perilously close to a supermassive black hole, the planet experiences such intense gravitational time dilation that 1 hour on its surface equals 7 years back on the main spacecraft. The crew witnesses this not as a theory, but as a visceral, terrifying reality. They see massive, slow-motion waves looming over the landscape, each wave taking hours to crash, while years of their own lives and the lives of those waiting for them vanish in an instant. This cinematic portrayal, grounded in real physics, makes the abstract brutally concrete. It shows us that time is not a background constant, but a malleable landscape with valleys where it flows slow and mountains where it races. And if a planet's gravity can create such a dramatic time differential, what other temporal wonders are hidden in the fabric of the cosmos? This cosmic speed limit is not just a barrier for rockets, it is the very architect of time's strangest behavior. The speed of light in a vacuum is the one constant in a universe of variables, an unwavering rule that everything else must obey. This constancy has a profound and counterintuitive consequence. As any object with mass accelerates closer and closer to this ultimate speed, from its own perspective, time begins to warp dramatically. The faster you go, the slower your clock ticks relative to a stationary observer. Distances themselves appear to contract in the direction of motion, a phenomenon called length contraction. The universe literally reshapes itself to preserve that sacred speed limit. To understand this, think of a journey to a star 100 light-years away. From Earth, that trip would take any signal, even light itself, 100 years to complete. But for an astronaut traveling at 99.9% of light speed, time slows down so much that the entire voyage might feel like only a few months. They would age mere months while centuries passed on Earth, effectively leaping into the future. This is the mechanism behind time travel to the future, not with a mysterious machine, but with sheer velocity. The most extreme perspective belongs to light itself. A photon, a particle of light, experiences reality in a way that obliterates our everyday concepts. Because it travels at the cosmic speed limit from the photon's point of view, time does not pass at all. The moment it is emitted from a distant star and the moment it is absorbed by your eye are the same instant. Its multi-billion-year journey across the universe happens in zero time. For a photon, the entire cosmos is compressed into a single, timeless point. This is not a poetic metaphor, but a direct prediction of Einstein's equations. The fabric of spacetime folds so completely at light speed that the concepts of before and after lose their meaning. This underpins the very real possibility of future time travel through high-speed journeys. A spacecraft accelerating to a significant fraction of light speed would become a time capsule for its crew, sheltering them from the relentless flow of time experienced by the rest of humanity. They would return to a planet that had aged decades or centuries more than they had. The engine for this journey is not magic but physics. The universe has built a backdoor into the future, and the key is velocity. But if traveling at light speed stops time, what happens in a place where light itself cannot escape? The answer lies in the heart of a darkness so complete it bends the rules of reality itself. That theoretical key to the future is not just gathering dust in an equation. It is being used right now by people living and working in orbit. Every astronaut aboard the International Space Station is, in a very real sense, a time traveler to the future. Hurtling around our planet at about 17,500 miles per hour, they are moving fast enough for Einstein's time dilation to take a tiny, measurable bite out of their personal timeline. For every 6 months they spend on the station, they age approximately 5 milliseconds less than their counterparts on Earth. It is a minuscule leap, a fraction of a blink, but it is irrefutable proof that high-speed motion literally slows the clock. They return to our world ever so slightly younger than they should be, having visited the future by a few thousandths of a second. Now amplify that principle to its logical, breathtaking extreme. Imagine a spacecraft built not for orbital loops, but for a true voyage to the stars. Its engines push it to a staggering 99% of the speed of light, a velocity where the universe's warping effects become profound. The crew sets a course for Proxima Centauri, the nearest star to our Sun, a distance of about 4.2 light-years. From the perspective of mission control on Earth, the round trip will take just over 8.5 years. But for the astronauts on board, time is flowing at a mere fraction of that rate. Due to the intense relativistic effects, their clocks might tick through only a single year. They live, work, and experience 1 year of life during the journey. When their ship finally breaks and returns to orbit Earth, they open the airlock to a world that has moved on without them. For Earth, 8.5 years have passed, families have aged, children have grown, history has unfolded. The crew, however, has only aged 1 year. They have not simply been in suspended animation, they have physically traveled 8.5 years into the future. They have left their own time behind. This is not science fiction magic, it is the direct, unavoidable consequence of physics. The velocity of their journey acted as a one-way ticket forward through time. There is no known law of physics that prevents this. The engineering challenges are, of course, monstrous, bordering on the impossible with our current technology. But the principle stands firm and unassailable. Time travel to the future is not a fantasy. It is a theoretical certainty waiting for an engine powerful enough to make it real. Yet this journey reveals a haunting asymmetry, a one-way street built into the cosmos. You can ride velocity into the future, but what about the past? Is there any way to turn the ship around? The journey into the future is a one-way street, and physics provides a compelling reason why. This irreversible direction is called the arrow of time, and it is governed by a fundamental cosmic rule known as the second law of thermodynamics. In simple terms, this law states that disorder or entropy in a closed system always increases. It never spontaneously decreases. This relentless march toward greater disorder is what gives time its unmistakable forward direction. It is the reason we remember the past but not the future. It is why a hot cup of coffee left on a table will always cool to room temperature, its heat dissipating into the air, never to spontaneously gather back into the cup. The most iconic example is a shattered wine glass. You can watch it fall from a table, shatter into 100 pieces and scatter across the floor. But you will never, ever witness those pieces leap from the floor, reassemble themselves in mid-air, and land perfectly intact back on the table. The universe does not run that film in reverse. The increase in entropy from an ordered whole to a disordered mess defines which way the film plays. This arrow was not always pointing. Scientists believe it was set in motion at the very beginning of everything, at the moment of the Big Bang. Our universe was born in an astonishingly specific state of extremely low entropy, a condition of extraordinary order and uniformity. From that pristine, ordered starting point, the only possible direction for the cosmos was toward greater and greater disorder, like a wound-up spring slowly unwinding across billions of years. Every process we see, from the fusion of stars to the beating of our hearts, is a consequence of that initial state unraveling. This leads to a profound and unsettling question. What would time even mean in a universe that had reached maximum entropy, a state of perfect uniform disorder often called the heat death of the universe? In such a cosmos where no energy gradients exist to drive any change, where everything is a lukewarm, featureless soup, would the concept of before and after have any meaning? Without change, without the constant increase of disorder, there can be no arrow. Time itself might become a directionless, meaningless dimension. Our experience of time flowing, of cause leading to effect, is not a feature of empty spacetime, but a direct consequence of the universe's ongoing and irreversible slide from order into chaos. But if the arrow of time points relentlessly forward on the grand cosmic scale, what happens when we peer into the quantum realm where the rules of cause and effect seem to dissolve? While the arrow of time gives our universe a clear direction, it also begs a monumental question. When did this grand, irreversible story actually begin? We now know with remarkable precision that our cosmos has a birthday. The universe is approximately 13.8 billion years old. This is not a guess, but a figure calculated through multiple, independent lines of astronomical detective work that all converge on the same answer. The most powerful evidence comes from the oldest light we can see, a faint afterglow that permeates all of space called the cosmic microwave background radiation. This is the cooled and stretched remnant of the first light that could travel freely through the universe, emitted when it was just a hot, dense soup of particles about 380,000 years after the Big Bang. By mapping the tiny temperature fluctuations in this ancient light with satellites like Planck, scientists can determine the universe's composition, geometry, and crucially, its expansion rate over time. This expansion rate, known as the Hubble constant, is like a cosmic speedometer. By measuring how fast galaxies are racing away from us and tracing that motion backwards, we can rewind the tape of cosmic expansion to a single point of origin. The math consistently points to that moment of beginning 13.8 billion years ago. To grasp the sheer scale of this timeline, imagine compressing the entire history of the universe into a single calendar year. The Big Bang happens at the stroke of midnight on January 1st. Our Milky Way galaxy forms in March. Our own solar system and Earth do not appear until early September. Dinosaurs roam the planet in late December but go extinct on the morning of December 30th. All of recorded human history, from the first civilizations to the present moment, unfolds in the final 10 seconds before midnight on December 31st. In this cosmic year, you and I and everything we have ever known are less than a heartbeat in the very last instant. This profound perspective establishes the grand stage for everything that follows. It is the ultimate timeline against which all other events, from the birth of the first stars to the slow death of the last ones, will be measured. It frames our existence not as the central event, but as a very recent, fleeting whisper in an epic that has been unfolding for billions upon billions of years. And if the universe has a definite beginning in time, does it also have a definitive shape in space? The answer is stranger than any geometry you learned in school. That definite birthday 13.8 billion years ago is known as the Big Bang, but the name itself is a cosmic misdirection. It was not an explosion that happened somewhere in a pre-existing space, like a firecracker going off in an empty room. Instead, it was the explosive emergence of space itself, and with it the very first tick of time. There was no before, because before requires time to exist. There was no outside, because outside requires space to exist. The Big Bang marked the origin of the entire cosmic arena, the stage, the actors, and the script all coming into being at once. To understand the sheer strangeness of this beginning, we must look at the very first moments. The Planck epoch is the name given to the first sliver of existence, from time 0 to about 10 to the power of -43 seconds. In this unimaginably brief span, the universe was smaller than a single atom and hotter and denser than anything we can possibly recreate. Here, our trusted laws of physics, Einstein's relativity, quantum mechanics, completely break down. Gravity, space, and time cease to behave as we know them, becoming a seething, chaotic quantum foam. It is a realm of pure potential where the concepts of cause and effect may not even apply. We simply have no scientific language to describe what happened during this epoch. It is the ultimate frontier of our ignorance. This leads to the most mind-bending question of all. What happened before the Big Bang? Given that time itself began at that moment, the question might be as nonsensical as asking what is north of the North Pole. There is no before because there was no time for anything to happen in. The universe did not appear within time, it appeared with time. This does not mean there was nothing, but rather that our familiar framework of past, present, and future has no purchase on that ultimate origin. It is a boundary to reality, a true beginning. Yet from that mysterious, lawless beginning, an event of staggering power unfolded, setting the course for everything to come. In the first fraction of a second after the Planck epoch, the universe underwent a process called cosmic inflation. Think of it not as a slow expansion, but as a hyperdrive jump. Space itself inflated faster than the speed of light, doubling in size over and over again in an eye blink. In less than a trillionth of a second, a subatomic speck of primordial universe was stretched to a size larger than our entire observable cosmos today. This incredible burst did two crucial things. First, it took the microscopic quantum fluctuations from the Planck epoch and stretched them to astronomical scales, planting the seeds that would later, under gravity's pull, grow into all the galaxies and clusters we see. Second, it ironed out the universe, making it remarkably smooth and uniform in temperature, which is exactly what we observe in the cosmic microwave background. Inflation was the setting of the stage, the moment the chaotic potential of the beginning was translated into a universe that could eventually produce stars, planets, and us. But if the universe began in a single, hot, dense state and has been expanding ever since, what is the shape of this grand arena we call home? Our universe's grand shape determines its ultimate fate, and science points toward two starkly different endings. The first, and currently the most likely based on our observations, is known as the heat death. Imagine a cosmos that continues expanding forever, driven by the mysterious force we call dark energy. Over trillions upon trillions of years, galaxies will be pulled apart, stars will exhaust their nuclear fuel and fade to black, and even the sturdiest structures, planets, asteroids, perhaps even black holes themselves, will eventually decay through a process called Hawking radiation. The universe will become a vast, ever-thinning soup of fundamental particles and radiation, spread so thinly that the temperature everywhere approaches absolute zero. This is the state of maximum entropy, the final victory of disorder. In this frozen, dark, and utterly uniform reality, no energy differences exist to power any process. Nothing changes, nothing happens. Without change, the arrow of time, which depends on increasing disorder, simply ceases to have any direction or meaning. Time as a measure of sequence and event would effectively end. It is not that clocks stop ticking, it is that the very concept of ticking loses all purpose in an eternal, featureless sameness. The opposite, more dramatic possibility is the Big Crunch. This scenario requires that the collective gravity of all the matter in the cosmos is strong enough to one day overcome the force of dark energy, putting the brakes on expansion and then reversing it. The universe would begin to contract, slowly at first, then with terrifying speed. Galaxies would rush together, the cosmic background radiation would blue shift into a searing heat, and space itself would shrink. All matter and energy would be compressed into an unimaginably hot, dense state, a singularity mirroring the Big Bang but in reverse. In this fiery collapse, the fabric of spacetime could be torn apart. Just as time began at the initial singularity, it could potentially end at this final one. The universe would not just be destroyed, it might be unmade, with the dimensions of space and time ceasing to exist. Current evidence, however, paints a colder picture. Measurements of distant supernova and the cosmic microwave background strongly suggest that the expansion of the universe is not slowing down but accelerating. Dark energy appears to be winning its tug of war with gravity. This makes the heat-death scenario the leading scientific forecast for our cosmic destiny, a slow, cold fade into oblivion where time itself dissolves into irrelevance. It is a fate of quiet extinction, not a fiery climax. But if time itself can potentially end, could it also be woven from something more fundamental, something that operates in discrete, indivisible chunks? If time can end in a cold, silent fade, could its very fabric be woven from the smallest possible threads? The search for that fundamental thread leads us to the ultimate limit of measurement, a unit so brief it defies human comprehension. This is Planck time, the smallest meaningful interval in the universe, lasting approximately 10 to the power of -43 seconds. To grasp this scale, imagine the time it takes light to cross a single proton. Now divide that unimaginably short span by a number with 43 zeros after it. That is Planck time. It is not just a tiny number, it is a boundary. According to our best theories of quantum mechanics and gravity, at intervals shorter than Planck time, the smooth, continuous fabric of spacetime we experience dissolves into chaos. The orderly stage of reality breaks down into a seething, turbulent froth physicists call quantum foam. In this realm, space and time themselves become fuzzy and uncertain. Tiny wormholes might blink in and out of existence, and the very geometry of the cosmos fluctuates wildly. The concepts of before and after, of here and there, lose all meaning. This reveals a staggering possibility. Time itself may not be a smooth, flowing river. Instead, the universe might operate in discrete, indivisible ticks, like the frames of a cosmic film or the pixels on a screen. Each tick would be one Planck time, the universe updating its state from one instant to the next. We do not perceive this granularity because the ticks are incomprehensibly fast. There are more Planck times in 1 second than there have been seconds since the Big Bang. Our reality would be an illusion of continuity, much like a movie appears smooth despite being a series of still images. This idea of a digital universe with time and space quantized into fundamental chunks is a major frontier in the quest for a theory of quantum gravity, a framework that would finally unite Einstein's relativity with the quantum world. While not yet proven, Planck time stands as a profound reminder that our intuitive sense of a continuously flowing present may be a beautiful macroscopic illusion. The deeper we probe, the stranger time becomes, and if time itself is granular, what does that imply for the most reliable timekeepers we have ever built? Your phone's map knows more about relativity than most people do. Every time you ask for directions, you are relying on a network of satellites orbiting high above the Earth, each one carrying an atomic clock of incredible precision. Those satellites are moving at thousands of miles per hour, and according to Einstein, that high speed alone makes their onboard clocks tick slower than clocks on the ground. But there is another factor. They are also farther from Earth's center of mass in a significantly weaker gravitational field, and weaker gravity makes clocks tick faster. These two effects, the slowing from speed and the speeding up from lower gravity, work against each other, but they do not cancel out. The gravitational effect is stronger. The net result is that time on a GPS satellite runs about 38 microseconds faster every single day than time on your kitchen counter. If the system's engineers did not deliberately program the satellite's clocks to tick slightly slower before launch and continuously correct for this drift, the entire network would fail within hours. Your navigation would be off by miles within a day. So every turn you take guided by that little blue dot is a silent testament to the fact that time is not absolute. It is a correction for reality's warped fabric. This bending of time is not just a feature of high orbit, it is woven into the very planet beneath your feet. If we could take a theoretical journey to the center of the Earth, we would find a place where gravity, in a strange way, vanishes. At the very core, the pull from the mass surrounding you cancels out. But getting there means passing through the immense gravitational field of the planet itself. Over our world's 4.5 billion year history, the crushing gravity at Earth's heart has slowed time relative to the surface. Calculations show that because of this, the planet's core is actually about 2.5 years younger than its crust. The center of our world is literally a time capsule from a slightly later moment in Earth's history. It is a difference born from pure gravity, a testament that time flows at different rates even within a single, seemingly solid object, and you are a time traveler in your own right every single day. When you get into a car and drive to the store, you are moving faster than your neighbor who stayed home. According to special relativity, your clock is now ticking infinitesimally slower than theirs. The effect is so vanishingly small it is impossible to measure with any conventional tool. For a 1-hour drive at highway speeds, the time difference would be far less than a billionth of a second. But it is real. It is a whisper of the same principle that lets astronauts leap milliseconds into the future. Your daily life is a constant, subtle dance with time dilation, proof that the universe's strange rules are not locked away in distant space. They are operating in the palm of your hand and under the hood of your car, quietly shaping the fabric of your reality with every passing second. The map on your phone is a quiet testament to a far deeper truth. We have been exploring time as something that bends and flows, but what if it is not a river at all? What if it is something far more solid and permanent? To grasp this, we must shift our perspective completely and embrace one of Einstein's greatest insights. He did not just show that time is relative, he proved it is a dimension as real and tangible as length, width, and height. We do not live in a universe of 3 dimensions of space plus time. We live within a single, inseparable entity called spacetime, a 4-dimensional continuum where every event has a unique address defined by where and when it happens. Think of it like a freshly baked loaf of bread. The entire loaf is the whole of spacetime, the complete history of the universe. Now slice that loaf. Each individual slice represents the entire universe frozen at one single, specific moment, all of space at a particular instant in time. As you move from the crust end to the heel, you are moving from the past to the future, viewing every moment of cosmic history laid out in a permanent, unchanging structure. This leads to a theory known as the block universe. In this view, the past, the present, and the future are not ephemeral. They all exist eternally and simultaneously, fixed within this 4-dimensional block. The moment of the Big Bang is just as real as the moment you were born, which is just as real as the heat death of the universe trillions of years from now. They are all simply different locations within the block. This utterly dismantles our most intuitive feeling about reality, the sensation of a flowing now, a moving present that sweeps the future into the past. If the block universe is correct, that feeling is an illusion, a trick of consciousness. Your entire life, from your first breath to your last, is already there in the block, a long, winding world line threading through the 4-dimensional structure. Your journey through time is not you moving through a flowing river, but more like the point of a needle moving along a thread that is already woven into a vast, timeless tapestry. You experience it moment by moment, but the entire thread exists at once. This is not just a philosophical fancy. It is the most natural interpretation of Einstein's equations of relativity, where time is treated mathematically as just another coordinate. It suggests that free will might be an experience within the block, not a power to change its structure. The future is not waiting to be written, it is already written, and so is the past. We are simply reading the book of our own world line, one unforgettable moment at a time. This raises a haunting and beautiful question. If all of time exists at once, what does that say about the moments we cherish, the memories we hold, and the choices we feel we make? That tapestry of time is already woven, yet we experience it as a vivid and undeniable present. But what is this present moment we feel so acutely? Neuroscience reveals a startling secret. The now you are experiencing is not the now that is actually happening. It is a carefully constructed illusion, a brief window of perception psychologists call the specious present. This is not the philosophical block universe, but the biological reality of your own brain. Your consciousness does not operate in real time. There is a processing delay, a lag between an event occurring in the world and your brain assembling it into a coherent experience of the present. This delay is roughly 80 milliseconds. In essence, you are living about 1/12 of a second in the past. Every sight, sound, and sensation you believe is happening right now actually happened a moment ago. Your brain is a master editor, taking this constant stream of slightly delayed information and stitching it together into a seamless narrative that feels instantaneous. It smooths over the gaps, synchronizes inputs from different senses, and presents you with a polished, unified experience of the present. This editing room is why, for example, you see a batter hit a baseball and hear the crack of the bat at the same instant, even though the sound takes longer to reach you. Your brain waits for the slower sound signal to arrive, then backdates it to align with the visual, creating a single, coherent event. Your present is not a point but a constructed span. This biological delay is not the same for all creatures. Different animals perceive the flow of time at radically different rates, a concept known as temporal resolution. It is measured in flashes per second, like the frames of a film. For humans, our flicker fusion threshold is around 60 flashes per second. Anything faster appears as continuous motion, which is why movies and television work. But for a common housefly, that threshold is around 250 flashes per second. To a fly, the world appears to move in extreme slow motion. Your hand swatting at it is not a sudden blur, but a slow, lumbering threat it has ample time to evade. A hummingbird, with its incredibly fast metabolism and wing beats, also perceives time in a more granular, slowed-down way. Conversely, larger, slower-moving animals like tortoises or elephants likely experience time as flowing faster, with fewer perceptual frames per second. There is no single, universal now. Your subjective experience of time's flow is a product of your biology, your metabolism, and the speed at which your nervous system can process the world. This blurs the line between the objective ticking of cosmic clocks and the deeply personal river of consciousness. The present you feel is a fragile, manufactured moment, a brief and beautiful illusion crafted by your brain from the raw material of a universe where all moments may already exist. Our brains construct a present moment, but the universe may be constructing time itself from something far more exotic. In 2017, scientists confirmed the existence of a form of matter so strange it redefines the word crystal. We are familiar with crystals like diamonds or quartz, where atoms are arranged in a repeating, orderly pattern in space, but a time crystal is something else entirely. Its atoms are arranged in a pattern that repeats not in space but in time. Imagine a ring of atoms that, when nudged by a tiny pulse of energy, begins to oscillate or flip its state in a perfect, predictable rhythm. A normal system would eventually lose energy to friction and stop. A time crystal, however, locked in a delicate quantum dance, will keep flipping back and forth forever, not in a steady state but in a repeating cycle, without ever absorbing any net energy from its surroundings. It is a perpetual motion machine, not of the impossible classical kind, but one permitted by the bizarre rules of the quantum world. This behavior breaks something physicists call time translation symmetry. In most physical systems, the laws are the same at every moment in time. If you perform an experiment today or tomorrow, you expect the same result. A time crystal explicitly breaks this symmetry because its state depends on the phase of its internal cycle. It has a built-in immutable rhythm in time, much like a spatial crystal has a built-in immutable pattern in space. The potential of this discovery is staggering, particularly for the field of quantum computing. The fragile quantum bits or qubits that power these machines are notoriously delicate, easily losing their special state through decoherence. A time crystal's inherent, stable rhythm could act as a perfect natural clock within a quantum computer, helping to synchronize operations and protect qubits from random noise. It could be the bedrock of stability upon which a reliable quantum future is built. Beyond engineering, the existence of time crystals forces us to confront a profound new layer of reality. We have seen that space can be granular and that time can be bent. Now we see that time itself can have a periodic structure, a kind of heartbeat woven into the fabric of matter. It suggests that the universe may not only be built from stuff that exists in space, but from processes that are fundamentally rhythmic in time. This is not just a new object to study, it is a new phase of existence, revealing that the dimension we call time might be more than a blank stage. It could be an active participant in the architecture of everything. The stability of a time crystal hints at a universe with built-in rhythms, but one of time's most famous puzzles involves not a steady beat but a broken symmetry. We must return to the twins, recall the paradox: one twin stays on Earth, the other travels to a star at near light speed and returns, finding their Earth-bound sibling much older. But if motion is relative, why isn't the situation symmetric? From the traveler's perspective, couldn't they say Earth rushed away and then came back, making the Earth twin younger? This apparent contradiction is the heart of the paradox, and its resolution is the key to understanding why time travel to the future is a one-way ticket. The flaw in the symmetry argument is subtle but absolute. The traveling twins' journey is not one of constant, unchanging motion. To complete a round trip, to leave Earth, reach a distant star, turn around and return home, the astronaut must undergo acceleration. They must fire their engines to speed up, later fire them again to slow down and reverse course, and finally brake to land back on Earth. The stay-at-home twin, however, experiences no such forceful change. They remain in a single, unchanging inertial frame of reference, feeling only the gentle, constant pull of Earth's gravity. This difference is everything. In Einstein's relativity, the laws of physics are the same for all observers in uniform motion, but they are not the same for those who are accelerating. Acceleration is absolute. You can feel it in your bones. It is this period of acceleration that breaks the perfect symmetry between the twins. The traveler feels the genuine, physical push of their engines during the turnaround phase of the journey. This experience is not relative. It is a concrete event that permanently distinguishes their path through the cosmos from that of their sibling. We can visualize this with a spacetime diagram, a map where the vertical axis is time and the horizontal axis is space. The Earth twins' world line is a nearly straight vertical line, tracing their steady progress through time at a fixed location. The traveling twins' world line, however, is a long, shallow triangle. It goes out at an angle representing high speed through space, makes a sharp turn at the distant star, the acceleration phase, and angles back to reunite with the Earth twins line. Here is the crucial geometric insight. In the strange geometry of spacetime, the longest path between two events measured by time is actually the straightest one. The Earth twin who took the straight, unaccelerated path experiences the maximum amount of time. The traveling twin who took the detoured, triangular path through spacetime literally travels a shorter distance through the time dimension. Their odometer of experienced time reads a smaller number. This is not an illusion or a clock malfunction. The astronaut genuinely ages less because their journey through the four-dimensional continuum of spacetime was by its very shape a shorter trip. The paradox dissolves. The traveling twin is unequivocally the one who returns younger. Their experience of acceleration provides the objective marker that their frame of reference was not equivalent to their siblings. This resolution is not just a clever trick, it is a foundational pillar of modern physics. It confirms that time dilation is a real, physical effect with measurable consequences, not a trick of perception. The universe keeps a precise, geometric ledger of every path taken through its fabric, and the final aging of the twins is the irrevocable entry in that ledger. It tells us that the flow of time is woven into the very paths we take, and that a journey through space is always, inevitably, a transformation of time itself. The resolution of the twin paradox rests on a universe with a clear, geometric ledger of cause and effect, but descend into the quantum realm, and that ledger dissolves into pure potential. Here, particles like electrons and photons do not possess definite properties like position or spin until the very moment they are observed. Before a measurement, they exist in a ghostly state of all possible outcomes simultaneously, a condition called a superposition. An electron is not here or there, it is both here and there with a probability cloud describing where we might find it. This bizarre behavior is not a limitation of our instruments, it is the fundamental nature of reality at its smallest scales. And when this quantum strangeness collides with our understanding of time, the results are nothing short of mind-bending. The most dramatic demonstration of this is the Wheeler delayed choice experiment, a thought experiment made real in laboratories. Imagine a single photon, a particle of light, approaching a barrier with two slits. In the classic double-slit experiment, if you do not measure which slit the photon goes through, it behaves like a wave, passing through both slits at once and creating an interference pattern on a screen behind them. It exists in a superposition of paths. If you place a detector at the slits to catch it in the act, it instantly collapses into a particle, choosing one slit, and the interference pattern vanishes. Now Wheeler asked a terrifying question. What if you delay that choice? What if you let the photon pass through the slits in its wave-like superposition, and only after it has already done so, you decide randomly whether to place the detector or not? Astonishingly, the results show the photon's behavior changes retroactively. If you choose not to measure after it has passed the slits, it produces an interference pattern, as if it knew all along it was a wave. If you choose to measure after it has passed, it produces a particle pattern, as if it had been a particle from the start. The measurement you make in the present seems to reach back in time and dictate what the particle did in the past. This is not science fiction, it is a verified experimental outcome. It suggests that at the quantum level, the arrow of time may not be fixed. Causality, the sacred rule that cause must precede effect, appears to soften. The universe may not decide on a definite history until it is observed in the present. It is as if reality is a cosmic choose-your-own-adventure book where the choices you make on page 100 determine what happened on page 50. This does not mean we can send messages to the past or change established history in a macroscopic sense. The effect is sealed within the quantum system. But it forces us to confront a staggering possibility, that the past is not a fixed, immutable record, but a tapestry of possibilities that only becomes fully woven when observed from the vantage point of the now. The flow of time, so concrete in our daily lives, may be an emergent property, a statistical average that smooths out the profound ambiguity at the heart of everything. The quantum realm suggests the past is not fixed until we look, but what if the present is not flowing at all? The most radical idea in modern physics proposes that time, as we experience it, may not be a fundamental part of reality. It could be an emergent illusion, a side effect of our particular viewpoint within a timeless cosmos. This is not science fiction, but a serious implication of our quest to unify general relativity with quantum mechanics. At the deepest level of description, where the fabric of spacetime is presumed to be quantized, the variable of time can vanish entirely from the equations. The most famous example is the Wheeler-DeWitt equation, a cornerstone of quantum cosmology. This equation attempts to describe the entire universe as a quantum object. In doing so, it produces a startling result. The time variable simply cancels out. The equation describes a static, unchanging quantum state of the whole cosmos, a universe where nothing happens because there is no time for anything to happen in. It is a timeless snapshot of all that is. This is profoundly unsettling. How can a theory that has no time possibly give rise to our vivid experience of seconds, years, and history? Physicists propose that time emerges or becomes meaningful through other processes. One leading candidate is quantum entanglement. When two particles become entangled, their properties are linked regardless of distance. Some theories suggest that the intricate web of entanglement between all the particles in the universe might generate a kind of clock. Changes in these correlations could create the appearance of a sequence of one thing happening after another, even though the underlying quantum state is timeless. From this perspective, the flow of time is not a river but a pattern of changing relationships within a frozen block. Another view ties time's arrow directly back to thermodynamics and our own limitations. We are macroscopic, classical observers made of trillions of particles trapped within the universe. We cannot perceive its pristine, timeless quantum state. All we can see is a coarse-grained, averaged view of the universe with high entropy, with increasing disorder. Our perception of time flowing from past to future may be a necessary consequence of our own thermodynamic nature, of being complex systems that constantly process information and remember the past but not the future. We are like readers who can only turn the pages of a book in one direction, mistaking that forced progression for the book itself being written as we go. But the book, the block universe, may be complete. If this is true, then your deepest intuition, the feeling that the now is real and the future is open, is a magnificent trick of consciousness, a story your brain tells itself to make sense of a reality that is, at its core, eternally still. It means that at the fundamental level, the universe just is. The Big Bang, the rise of life on Earth, and this very moment are all equally present in a single, breathtaking now. That timeless quantum snapshot is not uniform across the cosmos. Our universe is a tapestry of extreme environments, and each region ticks to its own rhythm. This variation becomes stark when we compare the densest knots of matter to the emptiest stretches of space. In the vast, nearly empty cosmic voids that stretch between the filaments of the cosmic web, gravity is at its absolute weakest. There is little matter to warp spacetime, and with weak gravity, time runs fast. A clock placed in the heart of a billion light-year-wide void would tick measurably faster than an identical clock here in our Milky Way, which sits within a modest galactic group. Conversely, in the monstrous gravity wells of dense galaxy clusters, where thousands of galaxies swarm in a haze of dark matter and hot gas, time is stretched and slowed. The universe does not have a single, synchronized clock. It has a chorus of them, each singing at a slightly different pitch depending on the local curvature of spacetime. This large-scale time dilation is not just a theoretical curiosity. It leaves subtle fingerprints on the light we observe. When astronomers look at a distant supernova in a far-off galaxy cluster, they are seeing an explosion that happened in a region where time itself was running slower relative to us. This can minutely affect how we measure the expansion rate of the universe, adding another layer of complexity to our cosmic calculations. Even the pristine light of the cosmic microwave background, the afterglow of the Big Bang, has traveled through this lumpy cosmic landscape for over 13 billion years. The photons that passed through dense clusters were delayed, their clocks slowed, while those that raced through empty voids arrived a little sooner. This creates tiny, specific patterns in the temperature map of the ancient sky, patterns that sophisticated telescopes are now trying to decode. The cosmic web is not just a structure in space, it is a structure in space-time. The universe expands, yes, but its very rate of time is a variable symphony, playing faster in the silent voids and slower in the crowded metropolises of galaxies. This grand variation hints that to truly understand the cosmos, we must listen not just to where things are, but to when they are happening. Even the most precisely plotted journeys can reveal a hidden hitch in the universe's rhythm. Decades ago, scientists tracking the Pioneer 10 and Pioneer 11 spacecraft, those intrepid robotic explorers sent toward the outer planets and beyond, noticed something deeply puzzling. As the probes sailed into the deep cold of the outer solar system, they were slowing down ever so slightly more than anyone had predicted. The discrepancy was tiny, an acceleration toward the sun weaker than a billionth of the gravity you feel on Earth, but it was persistent and real. This was the Pioneer anomaly. For years, it presented a nagging mystery. Had we miscalculated the gentle push of sunlight? Was there some unknown drag from microscopic dust? Or, most tantalizingly, was this a faint signal that our understanding of gravity or even the flow of time itself needed revision? Some researchers speculated that perhaps in the vast, quiet expanse far from the sun, the laws of physics underwent a subtle shift. Could a minute, unaccounted for time dilation effect, be altering the probe's trajectories? The implications were profound, suggesting our cosmic map might have hidden wrinkles. The eventual answer was more mundane, yet no less brilliant. Meticulous computer modeling revealed that the anomaly was caused by heat. Not from an external source, but from the spacecraft themselves. The radioactive thermoelectric generators powering the probes emitted a faint, anisotropic glow of thermal radiation. More heat radiated from the back of the craft than the front, creating a tiny but constant photon thrust, a gentle brake pushing Pioneer back toward the sun. Once this thermal recoil force was precisely quantified, the anomaly vanished. The case was closed, but the lesson of the Pioneer anomaly endures as a monument to scientific rigor. It demonstrates that in the cosmic quiet, even the whisper of escaping heat can masquerade as a fundamental mystery. More importantly, it underscores an absolute truth. Tracking an object's motion through space is one of the most sensitive tests of time and gravity we possess. To measure a spacecraft's velocity is to measure the ticking of the cosmic clock in that region of space. Any unexpected drift is a potential clue, a tremor in spacetime itself. The Pioneer's journey proved that to navigate the stars, we must account for every whisper, from the roar of relativity to the sigh of a warm circuit board. Physics maps the clockwork, but who reads the time? We have explored time as a bendable dimension, a quantum possibility, and a cosmic variable. Yet one profound mystery remains untouched by any equation: the raw, subjective feeling of a flowing present. This is the hard problem of consciousness as it relates to time. Science can describe the mechanics of a clock and the dilation of its ticks, but it cannot yet explain why you have a vivid, internal experience of a now that feels like it is moving from one moment to the next. Your brain is not a passive recorder of time. It is an active, relentless time machine. It stitches together the delayed signals from your senses into the seamless movie of the present. It constantly projects models of the immediate future, predicting the path of a ball, the next word in a sentence, and compares them to what actually happens, updating your story in real time. It rummages through the past, retrieving memories not as perfect recordings but as reconstructions, influenced by the present moment. This constructed narrative, this thread of remembered past, perceived present, and anticipated future, is your conscious experience of time. It is a story your brain tells itself to make sense of a chaotic stream of data. So we must ask a haunting philosophical question. If a tree falls in a forest with no one to hear it, does it make a sound? We can rephrase it for our cosmic journey. If a universe unfolds with no conscious mind to witness it, does time flow? Or does it merely exist? In a cosmos devoid of observers, the block universe would simply be a vast four-dimensional sculpture of events, complete and unchanging. The concepts of past and future would have no meaning because meaning requires a mind to do the meaning-making. The arrow of time from thermodynamics would still point, but there would be no one to feel its direction. Our conscious awareness may be the very ingredient that transforms a static block of space-time into a river of experience. We are not just inhabitants of time, we may be its authors, weaving the sensation of passage from the raw material of a timeless reality. This places us in a strange and beautiful dual role. We are biological entities obeying the physical laws of a bending, quantized time, while simultaneously being the conscious narrators of a story that gives those laws their emotional weight. The ticking of the clock and the ache of memory are two sides of the same cosmic coin. Our consciousness weaves the river of time, but physics draws a line in the cosmic sand that even imagination cannot cross. That line is the speed of light, the universe's ultimate speed limit. Yet within the mathematics of relativity, a strange and haunting possibility flickers the tachyon. This is not a real particle we have found, but a hypothetical one that lives forever on the other side of that line. A tachyon, by its very definition, would always travel faster than light. It could never slow down to light speed or below, just as we can never accelerate to reach it. The equations suggest that to achieve this, a tachyon would possess what physicists call imaginary mass. This does not mean make-believe, but a specific mathematical property that leads to utterly bizarre consequences. Most startling of all, the math indicates that such a particle would experience time in reverse. From our perspective, a tachyon's journey would appear to go backward in time. Its emission might be seen after its absorption, its effect occurring before its cause. This is where the speculative idea crashes into the bedrock of reality as we understand it. If tachyons existed and could be used to send information, they would shatter causality. You could, in theory, send a signal to your own past. Imagine a scenario where you receive a tachyon message telling you not to build the tachyon transmitter. If you heed the warning, you never build it, so the message could never have been sent. But if you ignore it and build the transmitter, you create the very message that told you not to. This is a classic paradox, a logical knot that reality seems to forbid. For this fundamental reason, most physicists believe tachyons are mathematical phantoms, not real constituents of our universe. They represent a forbidden zone in the plot of spacetime, a sign that the cosmos protects the integrity of cause and effect at all costs. The speculative existence of tachyons ultimately reinforces a profound truth. The speed of light is not just a barrier for rockets, it is the guardian of time's arrow itself, ensuring that the sequence of events maintains a consistent, unbroken story from past to future. Causality stands as the universe's ultimate guardian, but its walls may have theoretical cracks. Deep within the complex mathematics of general relativity, there exist solutions that allow for paths through spacetime so twisted they bend back on themselves. These are called closed time-like curves. If you could follow such a path, you would journey through space and time only to return to the very event where your trip began, meeting your past self in a loop without end. It is the blueprint for a time machine, not built from gears and steel, but from the warped geometry of the cosmos itself. Two theoretical structures could, in principle, create such a path. The first is a rotating black hole described by the Kerr metric. Unlike the simpler, non-spinning black holes, a rapidly spinning Kerr black hole has a region just outside its event horizon called the ergosphere, where spacetime itself is dragged around at incredible speeds. The mathematics suggest that within the inner depths of such a black hole, beyond a second boundary called the inner event horizon, closed time-like curves could exist. Here, the dragging of spacetime becomes so severe that the light cones, which define the possible future for any event, tip over until your future points directly into your own past. The second, more famous possibility is the wormhole, often visualized as a tunnel or shortcut connecting two distant points in spacetime. If one mouth of the wormhole could be moved at relativistic speeds or placed in an intense gravitational field, time would pass more slowly for it relative to the other stationary mouth. This would create a time difference between the two ends. Walking through the tunnel from the slower ticking mouth to the faster ticking one would not just be a shortcut through space, but a jump into the past of the destination. Both ends would then exist at the same point in space, but different moments in time, forming a closed time-like curve. The obstacles, however, are not just immense, they are likely insurmountable. First, you would need to stabilize the wormhole. According to the equations, the throat of a traversable wormhole would collapse instantly under its own gravity unless it was propped open by something possessing negative energy density, often called exotic matter. This is not antimatter, but a hypothetical substance that would create a kind of anti-gravity, repelling spacetime itself. We have no evidence such matter can exist in the stable, macroscopic quantities required. Then comes the grandfather paradox, the logical killer of time travel to the past. If you travel back and prevent your own grandfather from meeting your grandmother, you would never be born and thus could never have traveled back to prevent the meeting. It is a contradiction that seems to violate the fundamental consistency of reality. Some physicists, like Igor Novikov, propose a self-consistency principle to resolve it. This principle asserts that the laws of physics simply will not allow paradoxes to happen. Any action you take in the past must already be a part of established history. You could not change the past, you could only fulfill it. Perhaps your attempt to interfere is what actually caused your grandparents to meet in the first place. In this view, free will on such a journey would be an illusion, and the timeline would be a single, unchangeable loop. For now, closed time-like curves remain fascinating ghosts in the machinery of Einstein's equations, a reminder that our universe's laws contain hidden rooms we may never learn to enter. They are a testament not to what we can build, but to the breathtaking and often paradoxical landscape painted by pure mathematics. The theoretical loops of closed time-like curves hint at a universe where time might fold, but its ultimate fate may be one of violent, irreversible tearing. This brings us to the most mysterious force in the cosmos, dark energy, represented in Einstein's equations by the cosmological constant. This is not a force that pulls or pushes matter, but a property of empty space itself. A kind of anti-gravity that causes the very fabric of the universe to expand at an accelerating rate. For billions of years, gravity's pull held sway, slowing the expansion from the Big Bang. But around 5 billion years ago, dark energy became the dominant player and the cosmic brakes were released. The expansion began to speed up, and it has been accelerating ever since. This relentless acceleration does more than just push galaxies apart. It writes the final chapter for time itself. If dark energy's strength remains constant or grows stronger, as some models suggest, we could face a cosmic finale known as the Big Rip. Imagine a force so potent that it overwhelms every binding force in nature. First, the accelerating expansion would tear apart galaxy clusters, then individual galaxies. As the rip approaches, the fabric of spacetime within our own Milky Way would strain until stars were ripped from their orbits. In the final moments, planetary systems would be shredded. Then, planets themselves would be torn from their stars. In the last hour, stars and planets would be vaporized as the expansion force overcomes the gravity holding them together. In the final, unimaginable fraction of a second, atoms and even atomic nuclei would be ripped apart, spacetime itself would be torn asunder, and the universe would dissolve into a soup of disconnected fundamental particles, unable to ever interact again. In this scenario, time does not just slow to a stop in a heat death. It meets a definitive, violent endpoint. With spacetime itself torn apart, the framework for causality for one event leading to another ceases to exist. There is no longer a continuum where a before can lead to an after. Time as a dimension that orders events would literally end. The cosmic clock wouldn't just stop ticking, the clock face would shatter. This is a future with a final timestamp, a finite number of years from now when the story of the universe and of time itself reaches a sudden and absolute conclusion. It is a stark reminder that the same dark energy accelerating galaxies away from us today may be weaving the very conditions for time's ultimate destruction. The violent finale of a big rip is not the only possible ending, nor is a singular beginning the only possible start. While the Big Bang marks the earliest moment we can currently trace, some cosmologists dare to ask what might lie beyond that horizon. Could our universe be just one act in an infinite cosmic play with no true beginning and no final curtain? This is the realm of cyclic models where time stretches eternally in both directions. One compelling vision is conformal cyclic cosmology, proposed by physicist Roger Penrose. It suggests that our universe's far future and its distant past are, in a profound mathematical sense, identical. In the heat-death trillions of years from now, when all matter has decayed and only massless particles like photons remain, the universe becomes smooth, cold, and featureless. At this point, Penrose argues, the concept of scale loses all meaning. An infinite, cold, empty universe is mathematically equivalent to an infinitesimally small, hot, dense one. In this conformal geometry, the ultimate end of one universe can be seamlessly reborn as the Big Bang of the next, in an endless cycle of expansion and renewal. Time in this model has no start and no finish. It is a loop without a seam. Another idea is the bouncing universe, where our expanding cosmos is the rebound from a prior contraction. Imagine a previous universe that expanded, reached a limit, and then collapsed under its own gravity in a big crunch. Instead of vanishing into a singularity, quantum gravity effects at the moment of maximum density could act like a cosmic trampoline, causing the universe to bounce back outward in the event we call the Big Bang. Each cycle would last perhaps hundreds of billions of years, with time flowing continuously from one to the next. A key puzzle for any cyclic model is entropy. Our universe began in a state of incredibly low entropy, an extraordinary order that set the arrow of time in motion. If the universe has cycled forever, why didn't entropy reach its maximum an eternity ago? Some theories propose that each bounce or conformal transition somehow resets entropy, wiping the cosmic slate clean and allowing a new arrow of time to emerge. The evidence for these ideas remains speculative but tantalizing. Penrose and colleagues have searched for faint, circular patterns in the cosmic microwave background, which they interpret as gravitational wave imprints from collisions of supermassive black holes in the previous eon. While controversial and not widely accepted, such claims keep the debate alive. The central takeaway is humbling. Our confident timeline of 13.8 billion years may be just the current chapter in a story with no first page. The question of what, if anything, came before our Big Bang is not meaningless metaphysics, but active, cutting-edge cosmology. It forces us to confront the possibility that time itself may be without origin, an endless river flowing through an endless sequence of worlds. Our deepest cosmic theories find their proof in a silent laboratory. The most accurate clocks ever built by humanity do not have gears or pendulums, but clouds of atoms held in a state of quantum suspension. Since 1967, the very definition of a second has been untethered from the unreliable spin of our planet. Instead, it is anchored to the immutable rhythm of the atom. 1 second is officially defined as the time it takes for a cesium-133 atom to complete exactly 9,192,631,770 cycles of a specific microwave transition. This is not an arbitrary number. It was chosen to match the old astronomical second as closely as possible, but its source is profoundly different. It is a clockwork built into the fabric of matter itself, a heartbeat so steady it reveals the universe's hidden warps. An atomic clock works by using microwaves to nudge cesium atoms into a higher energy state. The trick is tuning the microwave frequency perfectly to match the atom's natural resonance. When the frequency is exactly right, the maximum number of atoms change state. This resonance is the clock's pendulum. By locking an electronic oscillator to this atomic pendulum, scientists create a timekeeping device of almost unimaginable precision. The latest optical lattice clocks, which use strontium atoms and visible light, are so accurate they would not gain or lose a second in over 15 billion years longer than the current age of the universe. This staggering precision turns these clocks into the most sensitive detectors of spacetime itself. They do not just tell time, they feel the gentle tug of gravity that alters its flow. In a landmark experiment, physicists at the National Institute of Standards and Technology placed two identical atomic clocks on shelves just 1 foot apart in height. After running for a while, they compared them. The clock on the higher shelf, experiencing a barely weaker gravitational pull, ticked ever so slightly faster than the clock on the lower shelf. The difference was a mere few hundred quadrillionths of a second, but it was measurable and exactly matched Einstein's predictions. These clocks can detect the time dilation caused by driving a car up a mountain or even by the subtle mass of a single snowflake. They are not merely instruments, they are witnesses, confirming that the ground beneath your feet is a region of slower time. This atomic precision is the silent engine of our modern world. Beyond enabling the global positioning system, it synchronizes the entire global financial network, time-stamping transactions to prevent chaos. It governs the flow of data across the internet and ensures power grids remain stable. Our digital civilization ticks to the rhythm of the atom, a rhythm that constantly whispers the truth of a bending, relative universe. In these chilled vacuum chambers, the grand cosmic drama of warped spacetime plays out on a scale of centimeters and nanoseconds, proving that the strangest facts of relativity are not distant abstractions, but the very framework of our daily reality. Atomic clocks measure a universe where time is relative, but step outside our solar system, and the very definitions of a day and a year are rewritten. On a planet like Earth, a year is a stately orbit around our sun, and a day is a graceful spin on its axis. But in the vast menagerie of exoplanets, these cycles become unhinged from our familiar rhythms. Imagine a world like Kepler 78b, a scorching lava planet that orbits its star in a blistering 8.5 hours. Its entire year from one spring to the next is shorter than a single workday here. A child born on such a world would celebrate thousands of birthdays before their first Earth year had passed. Their concept of aging, of seasons, of a lifetime would be a frantic blur of countless orbits. At the opposite extreme, picture a lonely, frozen world drifting in the outer darkness of its system. Its year, a single lap around a dim red dwarf, might take tens of thousands of Earth years. For a civilization emerging on such a planet, recorded history from its Stone Age to its Space Age might all occur within a single, endless seasonal cycle. Their astronomers would track the slow, glacial creep of their sun against the background stars, a celestial clock with a hand that moves once per epoch. But an even stranger fate awaits many of these worlds, especially those huddled close to their stars for warmth. They often become tidally locked. Just as our moon always shows the same face to Earth, a tidally locked planet has a permanent day side and a permanent night side. One hemisphere is bathed in eternal, scorching daylight, while the other is plunged into everlasting, frozen night. On such a planet, the concept of a day collapses. Its rotational day becomes exactly equal to its orbital year. The sun hangs motionless in the sky of the dayside, never rising or setting. Time itself would be experienced in a radical duality. On the blistering dayside, under the relentless glare of the star, the environment is one of chaotic, energetic fury. On the frigid night side, in the perpetual shadow, processes would slow to a near standstill, a world of frozen stillness. This creates a profound and literal time dilation between the two hemispheres, not from relativity, but from environmental extremism. Life, if it could exist at all, might huddle in the thin, crepuscular ring at the border, the terminator line, where a perpetual sunset or sunrise offers a sliver of tolerable conditions. Here, the sun would neither rise nor set, but hover eternally on the horizon. There would be no dawn to mark a new day, no dusk to signal its end. How would a society on such a world mark the passage of time? They would have no daily cycle, only the slow procession of seasons caused by a slight wobble in their orbit or the rhythmic pulsing of their star. Their calendars, their rituals, their very biology would evolve around a sun that never moves, in a sky where time is not a cycle, but a permanent geographic condition. Your experience of growing older would be irrevocably tied to which side of the world you were born on. Even our planet's own clock has been reset by deep time. The steady 24-hour day we rely on is not a cosmic constant, it is a temporary setting in Earth's long history. When Tyrannosaurus rex stalked the Cretaceous floodplain 70 million years ago, the planet spun faster on its axis. A day back then was only about 23 hours long. This meant a year contained not 365 days, but roughly 375. The relentless drag of the moon's gravity through the friction of ocean tides acts as a gentle but persistent brake on our planet's rotation. Over hundreds of millions of years, this tidal braking has stolen momentum, slowing the spin and lengthening our day by about 1.7 milliseconds per century. It is a change imperceptible in a human lifetime, but over the age of the dinosaurs, it accumulated into a lost hour every day. Their world turned quicker, their nights fell sooner, and their biological rhythms pulsed to a faster celestial metronome. But the changes were not just terrestrial. As Earth spun faster in that ancient past, our entire solar system was on a grand voyage through the galaxy. The Sun, with all its planets in tow, orbits the center of the Milky Way once every 230 million years or so. This period is called a cosmic year. When dinosaurs first appeared, we were in a completely different spiral arm of the galaxy. The night sky above them was utterly alien, devoid of the familiar constellations we know today, instead filled with different star clusters and nebulae. The cosmic environment itself was different. As our solar system bobs up and down through the galactic plane and moves through varying densities of interstellar gas, it could influence the flux of cosmic rays reaching Earth, potentially affecting climate and evolution over eons. This dual perspective is staggering. Time is not just a personal or planetary experience, it is layered. The dinosaurs lived by a shorter day, counted more days in their year, and looked up at a foreign galaxy. Their now is not our now. It reveals that the constants we build our lives upon, the length of a day, the face of the night sky, are themselves transient features in the slow, majestic ticking of cosmic and geological clocks. Our present moment is a fleeting snapshot in an album where every page shows a different time. That silent, ticking clockwork of the atom confronts its ultimate nemesis in the darkest corners of the cosmos. Black holes are not just gravitational monsters, they are time's executioners, and they have presented science with a paradox so deep it threatens to unravel our understanding of reality itself. It is called the black hole information paradox, and it pits the two pillars of modern physics, Einstein's general relativity and quantum mechanics, against each other in a battle with time at its core. According to the unwavering rules of quantum mechanics, information is indestructible. Every particle carries data about its properties, its spin, its charge, its quantum state. That information can be scrambled, transformed, or hidden, but it can never be truly erased from the universe. It is a cosmic ledger that must always balance. Now enter a black hole. Stephen Hawking showed that black holes are not completely black. Due to weird quantum effects at the very edge of their event horizons, they slowly evaporate, emitting a faint glow we now call Hawking radiation. This radiation is purely thermal, like the heat from a stove. It carries no information about what fell into the black hole. It is random noise. So imagine a book is tossed into a black hole. The book is incinerated, its atoms crushed into the singularity. Over eons, the black hole evaporates via Hawking radiation, leaving behind only that featureless thermal glow. The information contained in the book, the story, the words, the author's intent appears to be permanently deleted from the universe. The quantum ledger has been violated. Information has been destroyed. This is the paradox. Either quantum mechanics is wrong and information can be lost, which breaks the foundation of all particle physics, or general relativity is wrong in how it describes the fate of things inside a black hole. The stakes could not be higher, for this conflict points directly to a missing theory of quantum gravity, a framework that would tell us how time and space behave when both are pushed to their absolute limits. Proposed solutions are as strange as the paradox itself. One radical idea is the firewall hypothesis. It suggests that the event horizon is not a smooth gateway as Einstein predicted, but a searing wall of high-energy particles. Anything crossing it would be instantly incinerated, preserving information at the boundary before it could be lost inside. But this violates the principle of equivalence, a cornerstone of relativity which states that free falling through an event horizon should feel like floating in empty space. Another, more elegant solution comes from the holographic principle. It proposes that all the information about what falls into a three-dimensional black hole is not lost inside, but is actually encoded in a scrambled, two-dimensional form on the surface of its event horizon, like a cosmic DVD. The three-dimensional interior is a projection of that data. When the black hole evaporates, that information is slowly and chaotically released in the Hawking radiation. The information was never destroyed, just translated into a form we struggle to decode. This idea suggests that our entire three-dimensional universe, with its flow of time, might itself be a holographic projection of information stored on a two-dimensional boundary at the cosmic horizon. The black hole information paradox is more than a technical puzzle. It is a screaming clue that our current understanding of time, as a smooth, continuous dimension that ends at a singularity, is fundamentally incomplete. To resolve the paradox, we may need to discover that time itself, at its most basic level, is not a dimension at all, but a consequence of quantum information processing on a cosmic scale. The fate of a single bit of data falling into the abyss may hold the key to rewriting the story of time itself. The black hole information paradox forces us to question time's very foundation, but our most powerful telescopes perform a quieter, more profound kind of time travel every single night. Every glance at the stars is a journey into the past. The light from our own sun takes 8 minutes to cross the vast gulf of space to our eyes, so we see it not as it is, but as it was 8 minutes ago. This delay is the universe's gift to historians. It means the deeper we peer into space, the further back in time we see. The Andromeda Galaxy, our nearest large galactic neighbor, is a beautiful, swirling spiral of stars. But that light has been traveling for 2.5 million years to reach us. When you look at Andromeda, you are seeing it not as it exists today, but as it was when early hominids first walked the plains of Africa. A civilization living there right now, pointing telescopes at the Milky Way, would see our galaxy as a faint smudge from the dawn of humanity. Our view of each other is a haunting echo from a different epoch. This principle, called look-back time, is the fundamental engine of modern cosmology. It transforms our telescopes into the most powerful time machines ever conceived. The Hubble Space Telescope's most famous image, the Hubble Ultra Deep Field, is the ultimate demonstration. By staring at a seemingly empty patch of sky for over 11 days, Hubble gathered the faintest photons in the universe. The resulting image is not a map of space as it is, but a family photo album of the cosmos. It contains thousands of galaxies, each a smudge of light that began its journey when the universe was a fraction of its current age. Some of those galaxies are seen as they were over 13 billion years ago, mere infants forming their first stars in the primordial darkness. We are not just observing distant objects, we are watching the universe grow up. This ability to see cosmic history unfold in reverse, with more distant objects appearing younger and more primitive, is how we piece together the story of galaxy formation and the expansion of the universe itself. Every new deep-field image from Hubble and now the James Webb Space Telescope is like turning to an earlier chapter in a cosmic history book we are only just learning to read. Our present moment on Earth is unique, but the sky above is a mosaic of countless pasts, all visible at once. That profound look into the cosmic past reveals a universe where time is a variable landscape, but the most intimate time machine is the one inside your own skull. In moments of sheer terror or peak performance, your brain can hijack the flow of time itself. During a sudden car accident or a near misfall, survivors often report the world shifting into slow motion. The screech of tires stretches into a low groan, the shattering glass seems to hang in the air, and thoughts race with impossible clarity. This is not a trick of memory, but a real-time alteration of perception. Neuroscientists believe that in a crisis, the brain's amygdala triggers a state of hyper-alertness. It floods the system with stress hormones and begins recording sensory data at a much higher frame rate, like a camera switching from standard to ultra-high-speed mode. Your conscious mind, accessing this super-dense record of the event, experiences it as time dramatically slowing down. The clock on the dashboard did not actually tick slower, but your internal processor sped up, creating a subjective expansion of the moment between the perception of threat and the impact. This phenomenon is not confined to terror. Elite athletes describe entering a state of flow, often called being in the zone, where time seems to both slow down and vanish. A baseball hitter facing a 95-mile-per-hour fastball has less than half a second to decide whether to swing. In that sublime state, the ball appears larger and moves across their vision as if through syrup, giving them a perceived eternity to track its spin and path. Their brain is not processing faster out of fear, but through years of honed skill and intense focus, it filters out all irrelevant noise. It dedicates immense computational power to a single stream of information, making the crucial milliseconds feel luxuriously long. We see this even in controlled experiments. Skydivers in free fall, hurtling toward the ground at terminal velocity, were asked to read a numerical display flashing numbers at a rate too fast to normally perceive. During their jump, in that state of intense arousal and focus, they could accurately read numbers flashing significantly faster. Their brains were processing visual information at an accelerated rate, stretching their subjective second. Astronauts, too, report unique shifts in time perception. Floating in the silence of the International Space Station, watching 16 sunrises and sunsets every 24 hours, the rigid markers of earthly time dissolve. Many speak of a powerful cognitive shift called the overview effect, where the sense of past and future can compress into a profound, timeless present, focused on the fragile beauty of the planet below. These experiences highlight a breathtaking duality. Out there, time is bent by gravity and velocity. In here, it is stretched and compressed by consciousness. Your mind is not a passive clock, but an active interpreter, constantly negotiating between the objective tick of atomic vibrations and the subjective river of lived experience. The final frontier of time is not in the depths of a black hole, but in the 3-pound universe within your own head, where a moment of crisis can become an eternity, and a lifetime of wonder can feel like a single, timeless breath. Out in the silent ocean of interstellar space, the universe operates its own network of perfect timekeepers. They are called pulsars, and they are the corpses of massive stars that died in supernova explosions. What remains is a city-sized sphere of pure neutron star material, so dense that a single teaspoon would weigh as much as a mountain. This remnant spins at a dizzying rate, and from its magnetic poles, it fires out beams of intense radiation, radio waves, X-rays, or gamma rays like a cosmic lighthouse. Each time that beam sweeps across our line of sight, we detect a pulse, and the rhythm of these pulses is astonishing. Some pulsars spin hundreds of times per second, their flashes arriving with a regularity that rivals our most advanced atomic clocks. The consistency is born from the incredible stability of the neutron star itself. With the mass of a star compressed into a sphere just a dozen miles across, it possesses a rotational inertia so immense that nothing can easily slow it down or speed it up. Its tick is a fundamental heartbeat of the cosmos, unperturbed by the chaos that shaped it. This makes pulsars far more than celestial curiosities. They are the ultimate natural clocks scattered across the galaxy. By monitoring an array of these pulsars with radio telescopes, scientists have created a galaxy-spanning instrument called a pulsar timing array. The idea is breathtakingly simple. As a gravitational wave, a ripple in spacetime from a distant cataclysm like merging supermassive black holes passes through our region of the galaxy. It minutely stretches and compresses the fabric of space between us and each pulsar. This infinitesimal warping changes the distance the radio pulses have to travel, causing their incredibly regular ticks to arrive at Earth just a fraction of a second early or late. By tracking the correlated pattern of these tiny timing deviations across dozens of pulsars, astronomers can not only detect the gravitational wave, but also map its origin in the sky. It is like using the galaxy itself as an interferometer, with pulsars as the markers on a ruler light years long. This work has recently borne historic fruit, with international teams announcing the first evidence of a background hum of low-frequency gravitational waves, likely from the chorus of countless black hole mergers across cosmic time. But the potential goes even further. Just as we use man-made satellites for GPS, a future interstellar civilization could navigate the galaxy using pulsars. Each pulsar has a unique signature, its location, and its precise pulse period. By comparing the arrival times of pulses from 3 or 4 known pulsars, a spacecraft could triangulate its position anywhere in the galaxy with phenomenal accuracy. It would be a galactic positioning system built into the very architecture of the cosmos, a map written in timeless, rhythmic light. These spinning beacons are more than dead stars. They are the universe's own metronome, keeping time for events we are only beginning to hear, and offering a constant, rhythmic guide for any journey through the starry dark. We have journeyed from the steady tick of a kitchen clock to the timeless roar of the Big Bang, discovering a truth far stranger than fiction. Time is not a simple, universal river. It is a complex, malleable fabric woven into the very structure of reality and experienced in countless different ways. It bends under the weight of a planet and stretches near the edge of a black hole. It is a dimension as real as space itself, yet it may be an emergent illusion born from quantum entanglement and our own consciousness. We have seen its arrow forged in the fire of entropy, its speed guarded by the cosmic limit of light, and its rhythm kept by the dead stars we call pulsars. It has a probable beginning and several possible dramatic ends, from a cold fade to a violent rip. This journey reveals that our most intimate experience, the feeling of a moving present, is perhaps the greatest mystery of all, a story written by our brains upon the silent, four-dimensional block of the universe. So the next time you glance at a clock or watch a sunset, remember you are not just observing a measurement. You are touching the edge of a cosmic mystery, a fundamental force that shapes everything from the orbit of galaxies to the beat of your own heart. Cherish the moments in this vast, strange timeline, for your conscious now is a rare and fleeting gift in an eternity of silent spacetime. If you found this exploration as fascinating as we did, be sure to subscribe. Our journey through the universe's deepest secrets has only just